All right, let's try this again. I won't tell you how many times I've tried to record this. I will tell you they've all been over 5 minutes. So enough of me wasting time. I have my coffee. I'm Morgan Nasser. I work at the Cyclotron Institute at Texas A&M University under Dan Melkonian. Our group studies physics beyond the standard model, specifically the weak interaction, which, as you know, governs beta decay. Beta decay is a three-body decay. It spits out a beta, a neutrino, and a daughter. The neutrino is kind of a pain in the butt to measure. Unfortunately, that's what we would like to measure, the beta and the neutrino. Specifically, so we can measure A beta nu, which gives us the angular correlation between the beta and neutrino. But because the neutrino is a pain in the butt, we would measure something else instead, the daughter. But this is also a pain in the butt. So we let the daughter decay into a granddaughter and proton. Now the proton is much easier to measure, and if we know what the proton did, we know what the granddaughter did. If we know those two, we know where the daughter was. And if we know where the daughter was, we know the neutrino and the beta. Can you tell I'm caffeinated by now? So, back to business. Beta delayed proton emitters. That's why we're measuring them. Now, who does that? Well, all of these colored ones here, as you can see, and feel free to pause at any moment so you can actually read this in detail rather than listening to my almost comical explanation, but very enticing description of everything. 32 argon will be the isotope of interest that we will measure first. Now, little disclaimer, we would like to do this at the Cyclotron Institute, but we don't have radioactive beam. We would love to use the world's largest spinning trap, which is our group's design and unique in the world, and also has 4 pi detection, but we don't have that luxury. So instead, we entered a collaboration with a group in France about 2, 3 years ago, and they have beam time at CERN. So that's where we're doing this, at least to begin. And at some point, we're working on getting the radioactive beam at the Cyclotron Institute. Unfortunately, that'll be beyond my PhD, so good luck to them. But anyways, so the experiment is shown over here in the lower left. I took too much time to explain last time, so I'll be very brief about it this time. The purple are silicon detectors. The pink is a scintillator. And the red track, which I drew on there for the guide of eye, is a proton. The blue is a beta. The orangish brown circle is mylar catcher foil. 32 argon will be shot onto the catcher foil, and then it will undergo its beta delayed proton decay. Spits out the betas and the protons. Betas go to the scintillator. Protons go to the silicon detectors, and boom, we measure proton energy spectrum from the silicon detectors triggered off of the betas. So how do we go about simulating this? It's a number of things, actually. So there's an R matrix code that, well, as the name implies, does R matrix calculations and an assortment of other things so that it does the beta delay proton decay. That gives us, amongst many other things, specifically the beta and protons, directions, energy, yada, 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 which is important because then we put the betas into Penelope, which is a Monte Carlo simulation mm, bunch of code project, whatever you want to call it. And so with that, which stands for penetration and energy loss of positrons and electrons, as you can see here at the bottom of the screen, is basically our Jant for the betas. Now, the reason we're doing this is because, well, the betas are very important to this experiment, and it's high precision frontier experimentation. And so if we can do these simulations better, we should. So Penelope will handle the betas, and this will also complement an independent analysis done by the France group, which they have 1 or 2 people on, where it's exclusively Jant, just Jant, everything, betas, protons, that's it, Jant, which, as everybody knows, is wonderful, and it works very well. But Penelope is deemed to be better than Jant at tracking and handling betas and photons, and now I'm starting to ramble, and this is how I lost too much time last time, so I'll be very brief about this. Jant and Penelope are different. Proof for that, top right. And probably you've seen Eric Aboud's mentioning of this too, I think, because he asked me for some material, and so maybe he showcased some of that too. But yes, Jant and Penelope are very different in how they handle things, and consequently the results are also different. And not just different, but visibly different. So in this top right plot, you can see the energy spectrum deposited into the scintillator for electrons that were going up. This is not the specific wizard experiment. This is a benchmark. It's visibly different. So that's that. That's why we're feeding things into Penelope. It's great. And then the protons go into Jant because Penelope doesn't handle protons. Otherwise, we'd be doing everything in Penelope. So energy spectrum. What do they look like? Well, they look kind of like this plot on the lower left for the protons, but kind of more so like this one in the middle. And the main difference between this is detector resolution. I mean, the one in the lower left is from a preprint that is just very low detector resolution, so it's a washed Gaussian at that point for each peak. But anyways, I never even described the Doppler shifting. So if beta goes this way and neutrino wants to go in roughly the same direction, then the daughter is going to try and go that way, statistically by majority. That's what I'm implying. So if then the proton also goes this direction, it gets kicked forward, more energy. So Doppler shift in the energy. If the vice versa happens, that is to say, proton goes the other direction that the daughter was going, or translated same direction as the beta, then it gets Doppler shifted down. And so experimentally, the way you would see this is the beta would go to the scintillator, and if the proton goes to the silicon strip detectors closer to the scintillator, we say that is a same hemisphere event, in which case the proton energy spectra read from that should be Doppler shifted down, and vice versa for opposite. So anyways, now that I've explained that, we can get to what we're trying to get at, like the main bulk thing out of this. We can have same and opposite hemisphere spectra. They will be shifted from one another. The difference in between those two spectra is a gauge on A beta nu. Because again, A beta nu is the angular the angular correlation between the beta and neutrino angle. I already said angle. So if A beta nu is less than 1, or yeah, less than 1, then it will be the spectra will be closer than the case where A beta nu is 1. And I never explained this because I've just been speed racing this. So A beta nu is 1 empirically. It looks like 1, and it's just kind of assumed there are no scalar currents. We're looking for scalar currents in the decay. That's the name of the game. If we find within precision, again high precision, 0.1%, that A beta nu is less than 1, there's physics beyond the standard model. That means there are scalar currents. Scalar currents, which to this day have just been assumed to be non-existent for no reason other than just observation. So that's what we're going for. Now to wrap things up, yeah, Jayant and Penelope are different. There's proof in the pudding here. And the simulations that are made here to go into the analysis of experimentation, which will be done this summer at CERN, are going to be wrapped up pretty soon, which is great. And there'll be other analysis, but like as far as this work goes, that's the bulk of it. Thanks for listening. If you have any questions, Nasser Morgan at tamu.edu. I said .com last time. It's edu. Nasser Morgan at tamu.edu. Questions?